Hello and welcome back for the second part of the talk, where I will be discussing the proofs of the main theorems and some open questions. Before I recall the statements of the main theorems and give their proofs, I would like to quickly recall the main points from talk number 1. Let's recall that we consider the four-manifold X closed, and then we removed a four-ball from it to get a four-manifold X circle with boundary S3. Given a knot K in S3, we consider smooth surfaces sigma properly embedded in X circle and with boundary the knot K. The question that we ask is then the following. Given such a closed smooth four-manifold X and the knot K, and fixed a homology class alpha, what is the minimum genus of a surface sigma smoothly and properly embedded in X circle with boundary the knot K and sitting in the homology class alpha? A special case is when you can choose sigma to be a disk. In such a case, we say that the knot is slicing X. So K is slicing X if it is the boundary of a smoothly embedded disk in X circle. If moreover you can choose such a disk to be null homologous, we say that the knot is H slice in X. Both notions are a generalization of the classical notion of sliceness. We now turn to Theorem 1. Before restating it, I would like to quickly recall the Oshvat-Szabo mixed invariant. If X is a smooth closed four-manifold with B2 plus greater than 1, and S is a spin-C structure on X, then you can define the Oshvat-Szabo mixed invariant as follows. You start from the four-manifold X, you remove the interior of two four balls, so that you get a cobordism from S3 to S3. Then you break the cobordism into two parts, X1 and X2, by choosing an embedded three-manifold N with some extra properties. Such a three-manifold is called an admissible cut by Oshvat and Szabo. The first cobordism X1 will give you a map on the negative flavor of Hegarth-Floer homology, HF minus. And the image of the map will be contained in HF minus red of N, the reduced homology. HF minus red of N is canonically isomorphic to HF plus red of N. And finally, X2 gives a cobordism map on HF plus. So we get a map with target HF plus of S3. If you compose all these maps, you get a map from HF minus of S3 to HF plus of S3, which is by definition the Oshvat-Szabo invariant of XS. There is a similar story if X is a four-manifold with boundary. In such a case, instead of removing the interior of two four balls from X, you just remove the interior of one four ball, and you get a cobordism from S3 to the boundary of X. As before, you choose an admissible cut, so the cobordism is split into two cobordisms, X1 and X2. You define maps as before, and the composition of all the maps is now a map from HF minus of S3 to HF plus of the boundary of K, of X. And this is defined to be the Oshvat-Szabo invariant of XS. We can now state again Theorem 1. suppose that X is a closed Four manifold with B2 plus greater than 1 and non-vanishing Ashvat-Szabo invariant. And let sigma be a smoothly embedded surface in X circle with boundary denote K and positive genus. Then under some technical assumptions that I will not discuss, there is an inequality involving the genus of sigma and the nu plus invariant of the mirror of K, which comes from Hegardt-Floer homology. And we call such an inequality an adjunction inequality. The reason why we call it an adjunction inequality is that such an inequality is in fact a generalization of Ashvat-Szabo's adjunction inequality for closed surfaces. So in Ashvat-Szabo's theorem, the difference is that they deal with a closed surface rather than a surface with boundary denote K. So of course, the nu plus invariant doesn't appear anymore in the formula because there is no knot anymore. Before moving to the proof of theorem 1, I would like to mention that in the adjunction inequality, in the second theorem here, we do not require X to be closed. We just require sigma to be closed. The strategy of the proof for theorem 1 is to somehow reduce it to the case of a closed surface, and then we apply Ashvat-Szabo's adjunction inequality. Let's give more details. We start from a surface sigma in X circle with boundary denote K. Then we look for a four manifold Z with a surface F sitting inside it with boundary the mirror of K. If we have that, we can glue Z to X circle and the surface F to sigma, so that we get a closed surface in a four manifold. And if the Ashvat-Szabo mixed invariant of the new four manifold is still non-zero, we can apply Ashvat-Szabo's adjunction inequality. The first attempt that we try for Z and F is to choose Z, the easiest possible. For Z, we choose the easiest possible for manifold, namely the four ball. And for F, we choose a genus minimizing surface for the mirror of K. In such a case, the four manifold that we get from the gluing is X, which by hypothesis has non-trivial Ashvat-Szabo invariant, so we can apply immediately the adjunction inequality, and we get the following inequality. This is already interesting, but it is not as good as the one that we want to prove, because the slice genus of K is always greater than or equal to nu plus of the mirror of K, and it is often strictly greater than it. So the inequality involving nu plus of the mirror of K will give better bounds. In order to get it, we have to glue a four manifold Z and a surface F in a slightly more interesting way. So we, in the first attempt, we chose Z to be the easiest possible for manifold. We now try to choose F to be the easiest possible surface, namely a disk. And we can do it if we use a two-handle attached along K as our four manifold Z, in which case we can choose F to be the core of the two-handle. The problem that may arise from this choice is that the four manifold resulting from the gluing may not have non-vanishing Ashvat-Szabo invariant, so we have to check that. So we start from X circle with boundary of X circle, which is also S3. In order to define the Hirschsprung sub-invariant, we remove the interior of a 4-ball, and then we choose an admissible cut. And the Hirschsprung sub-invariant is a map from HF minus of S3 to HF plus of the boundary of X circle, which is again S3. Then we want to glue the 4-manifold Z, which can be interpreted as a cobordism from S3 to some surgery on the knot K. Here we choose the surgery framing, the surgery parameter to be negative n, where n is a non-negative integer. Then it turns out that the Hirschsprung sub-invariant for the glued up 4-manifold is the composition of the Hirschsprung sub-invariant for X circle and the cobordism map induced by Z. Moreover, one can check that in order to have the Hirschsprung sub-invariant of the glued up 4-manifold non-vanishing, it is sufficient to require that the cobordism map induced by Z be non-vanishing on the bottom element of the tower of HF plus of S3. Whether the cobordism map is non-vanishing on this bottom element is governed by the d-invariance of the surgeries. And it turns out that the optimal choice here is n equal to 2 nu plus of the mirror of K. For such a choice, we have non-vanishing Hirschsprung sub-invariant. So when we apply the Hirschsprung sub-adjunction inequality, we get exactly the inequality that we were looking for. So this concludes the sketch of the proof of theorem 1. We now move to theorem 2. Let me restate it. Let X and W be closed symplectic 4-manifolds with B2 plus congruent to 3 mod 4. Suppose that the mirror of K bounds a non-null homologous disk delta in W circle with non-negative self-intersection. Then K is not H-slice in X. The proof of the theorem goes by contradiction. We assume that K is H-slice in X, so it bounds a disk D2 in X circle. But on the other hand, we know that the mirror of K bounds a disk delta in W circle. So if we glue the two 4-manifolds together and the two surfaces together, we get a sphere embedded in X circle union W circle, which is the same as X, oops. Okay, here I am. Which is the same as the 4-manifold X connected sum W. In fact, after possibly blowing up, one can assume that such a two-sphere is zero-framed, and the fact that delta is not null homologous implies that the sphere is also not null homologous. From here, one can apply a theorem of Fien-Tuchel and Stern that says that such zero-framed spheres do not exist, is the Seiberg-Witten invariant of the 4-manifold, which is X connected sum W, is non-vanishing. Unfortunately, we cannot apply Fien-Tuchel-Stern's theorem verbatim here, because the cyber-Witten invariant of the connected sum of such two manifolds is always vanishing. So one could try instead with the Oshpat-Szabo invariant, but unfortunately that vanishes as well. So instead, we use Bauer-Furuta's refinement of the cyber-Witten invariants, which have the advantage that they are non-vanishing for connected sums of symplectic 4 manifolds with P2 plus congruent to 3 mod 4. Then using that invariant, we prove a version of Fien-Tuchel and Stern's theorem for the Bauer-Furuta invariant. And so we get a contradiction from the existence of a zero-framed sphere. Let's now move to the proof of the last theorem, theorem 3, which is based on Furuta's 10/8 theorem. Let's recall Furuta's 10/8 theorem. This states that if X is a closed spin and indefinite 4 manifold, then its second Betti number is greater than or equal to 10/8 times the signature of X plus 2. There is an improvement of that theorem by Hopkins, Lin, Shi, and Xu, where the plus 2 is upgraded to a plus 4 as long as B2 of X is not 0, 2, and 22. Donald and Vafaei used Furuta's theorem to give an abstraction to classical sliceness. Our theorem 3 is a generalization of their theorem. After Donald and Vafaei, Twang improved the result using Hopkins, Lin, Shi, and Xu's improvement of Furuta's theorem. What we do is to generalize Donald and Vafaei's proof to spin for manifold. Suppose that K is H-slice in a spin for manifold X, and that the zero surgery on K is the boundary of a spin to handle body W. Then if the sum of the Betti numbers is not 1, 3, or 23, there is an inequality involving the sum of the Betti numbers and the difference of the signatures. Let me give an outline of the proof. We consider V the complement of the H-slice disk in X. The key point of the proof is that the boundary of V is the zero surgery on K, and both spin structures on the boundary of V extend to the whole 4 manifold. This implies that if you take the closed 4 manifold minus V union W, this is actually a spin 4 manifold because you can start from a spin structure on W. This will restrict to some spin structure on the zero surgery of K, and then you can extend that spin structure also to negative V, because you know that every spin structure on the boundary of V also extends to V. Then you apply Furuta's 10/8 theorem to minus V union W, or better, you apply the improvement by Hopkins, Lin, Shi, and Xu. Finally, I would like to spend some time discussing some open questions. I will start by recalling that a consequence of theorem 2 is that H-sliceness can detect exotic pairs. So there exists an exotic pair of manifolds X, X prime, such that their sets of H-slice knots are different. We can ask whether we can find an exotic pair that is detected by sliceness as opposed to H-sliceness. and we do not know the answer. This question is quite challenging, mainly because obstructing sliceness for every homology class seems to be much harder than obstructing sliceness just in the zero homology class, that is H sliceness. Moreover, there is an extra complication coming from the fact that we do not really have examples of potentially non-slice knots in some exotic four manifold. This is because our main source of example comes from the K3 surface, and we don't know whether every knot is sliced in the K3 surface or not. We proved that if a knot has a knotting number at most 2, then it is slicing K3, and Mukherjee proved this result for a knotting number at most 4. So this shows that if you want to find a knot that is not slicing K3, then it should be pretty complicated. Moreover, there's another interesting consideration here, that is that K3 is indefinite, spin, and symplectic. The fact that K3 is indefinite seems to point towards the fact that many knots should be sliced in K3. This is because for other indefinite four manifolds like S2 cross S2 and CP2 connected sum CP2 bar, every knot is sliced in them. On the other hand, K3 is spin and symplectic, and this poses strong restrictions on H sliceness, for instance. So the mystery of question 2 to me lies in the fact that K3 has both natures of an indefinite four manifold and a spin symplectic four manifold. Let's go to the last open question that I'd like to discuss, which concerns the dichotomy between smooth and locally flat. The question is whether every closed smooth four manifold X admits a topologically but not smoothly H-slice knot. We know that the answer is yes for some four manifolds, for instance, for S4, where it is well known that topological and smooth sliceness are different concepts. It is known also for CP2. This is a consequence of a work of Livingstone. And in our work, we prove it for K3. So interestingly, CP2 is a definite four manifold and K3 is indefinite. So we ask whether it is always true that you can find a topologically but not smoothly H-slice disk, H-slice knot in a four manifold. However, I would like to remark that the same question for sliceness, as opposed to H-sliceness, has a negative answer, because for the four manifolds S2 cross S2 and CP2 connected sum CP2 bar, all knots are smoothly sliced and hence topologically sliced. So here there is no difference between smooth sliceness and topological sliceness. This is the end of talk 2. I hope you enjoyed it. Thanks very much for listening both talks, and have a wonderful day. Bye.